Hello everyone, welcome to the platform of Unacademy, India's largest online learning platform where you get the opportunity to learn from India's best and top educator. So I welcome you all to this session. Let me check the things. So once again, I welcome you all to the session of Unacademy, in which this session is actually of Vapour Power Cycle. This is a part two, and part one we have discussed. So this part 2 will be focusing on the vapor power cycle regenerations concept, as well as we are going to solve some of the PYQs so that we will be confident enough to apply those concepts what we have learned in part 1 and what we are going to learn in this part 2 with the confidence, right? So let's start. So this is a brief introduction about myself. If you don't know about me, then my name is Vidyapati Kumar, and I have a 4+ year of teaching as well as research and development experience. I have done ME from Jadavpur University, and I have worked at CSIR, Central Institute of Mining and Fuel Research. I've qualified GATE twice, and I'm the author and co-author of various papers, research papers of national and international journal of repute. If you have a keen interest about the research works, do search about my work and study about them. You can follow me at Unacademy Learning app at the rate of v.ksir. So this is what is the brief introduction about myself, and this is going to be the part two of Vapor Power Cycle. What we have been started in Vapor Power Cycle part one, what we have seen the things like the reheat things and the basics concept of why we use the thermodynamic cycle. What is the thermodynamic cycles? What is the implications of these things? What is the Rankine cycle? How the Rankine cycles work? As well as apart from that, later on we just compared with the Carnot cycle, why we cannot use the Carnot cycle, why there is a use of the condenser. These things, these important concepts we have dig into that, and these things, like after that we work on the reheat concept. And this session we are going to focus on the regeneration, as well as we will be solving a lot of previous year questions, so that you will have a confidence after attempting this lecture. I am damn sure that you will be have a confidence to solve any question of Vapor Power Cycle. So I welcome you all to this session. So you can download the Unacademy Learning app, and it has the benefit because in this app there is a paid classes. Paid classes are there, that is a plus subscription, and there is a free classes. So in the free classes, that is actually known as special class, you can if you haven't downloaded the Unacademy Learning app, do download it, because I am taking the special class which is actually free. And in this special class I am teaching strength of material from the scratch. I am going to set your foundation, so that if your foundation would be good, then you can jump from strength of material to the design, to the various design things, and to the and you can attempt all the questions of ESE and GATE. So I will trying my level best to give you the good foundations. You can join my courses of strength of material there. And uh, and you can, if you want, you can actually go for a plus subscription, because it has a lot of benefits. There is a complete coverage of the syllabus would be there, 100% coverage of the syllabus would be there, as well as if you have you have opportunity to do the classes of almost all the educator. One subscription give you can do the classes of all the educator, as well as one subscription give you the benefit of two, that is you will be enrolled in GATE and ESE subscription. As well as you have a daily live classes, you have the opportunity to interact with your desired educator, what from whatever educator you want to study, and you will be having a doubt clearing sessions. That educator will help you to clear your doubt, as well as there is a test and live quizzes will be there. Structured courses are there, courses are structured, and whatever the content will be there in this Unacademy learning app, everything will be of unlimited access. As well as you have the chances, you have the opportunity to fix a personal coach and to choose a personal coach, and this personal coach will help you to fetch a good marks and liable to help you for the throughout GATE and ESE preparations. It will be also that question and answer practice would be there at that platform, as well as the study tracker would be there. What is your pros, what is your cons, which subject area you have a problem, and these mock tests and these everything would be the study tracker would be there, as well as the benefits of the plus would also be there. So these are the top educators at this platform, and Unacademy has a lot of batches, and the branches, for the branches the courses are there. For example, the mechanical, civil, CS, IT, instrumentation, production, industrial, chemical, mathematics, everything. So you can actually go for this, right? And if you're planning for a plus subscription, or if your any peers or any friends are planning for a plus subscription, do share. And the prices are like 5,000 for a 1 month, for a 3 month it is 12,500, for a 6 month it is 20,000, and for a 12 month it is 25,000. So if you're if you can do for the go for a 6 month or a 12 month plan, and whichever you are applying, you will get a 10% off. Okay, so you will get a 10% off, and when you will get a 10% off, discounted amount would be 22,500, and you will save the money. As well as I will provide my personal mentorship, and I will help you throughout the GATE and ESE preparation, so that you can fetch a very good marks. Apart from that, you have another plan for 24 months. For example, if you are in second or a third or a fourth year, you can always opt for a 24 months, and the cost is 30,000. But if you will use my code SIRVK, SIRVK, then you will get a discount, and the discounted amount is 27,000. So yeah, you are saving the money. And as well as the 10% discount, apart from the 10% discount, I will help you throughout the preparation. So go for any plan. If you can afford, you can go for any plans, and this is approx like 37 rupees per day, 60 rupees per day. So you can choose the plan accordingly, and do the plus subscription. So let me check the comment box once again. Okay, good afternoon, Asis. Asis, I will try to finish everything in this lecture. So maybe this lecture may be of 3 hours. So please stick with me. If you will stick with me, I will be able to finish everything. Good afternoon, Shivam ji. Good afternoon. Okay, so चलिए तो स्टार्ट किया जाए सेशन को. Hmm. But before starting the session, I want to I want to have a quick revise what I have given you in the part one. Okay, because everything is very much linked, and just I will take a short duration of time to have a quick revision. Okay, so see here. So we have seen in the part one of the Vapour power cycle, we have seen about the thermodynamic cycle. Why we need a thermodynamic cycle? Why we need a thermodynamic cycle? Because, and we have seen that wherever there is a case that in which we want from initial to final state, we want like all those cycle or processes which initial and final state are same, that is called as thermodynamic cycle. And why we need thermodynamic cycle? Because there is a continuous conversion of heat from work and work from heat. Okay, so after that, what we have seen, there is a concept of heat engine and the heat pump, right? So what is the heat engine concept? What is the concept of a heat engine? Concept of a heat engine is that the cycle or cyclic process in which like you are converting the heat is converted into the work, right? So heat is converted into the work, that is known as heat engine, right? What about the heat pump? What about the heat pump? Sir, work is converted into heat. Work is converted into heat, right? So in either of the cases, what we have seen, that since heat engine cycle produces mechanical power, right? Heat engine cycle produces mechanical power, hence they are known as power cycle. And what are the types of power cycles, sir? Power cycle types are vapor power cycle and gas power cycle, right? So this is just a quick revision, just a quick revision is there. And see, what is the thing that we have seen? Power cycle. Power cycle is divided, classified on the basis of the phase, on the basis of the phase. Clear? So it is divided on the basis of the phase. It is classified on the basis of the phase. Now see, what is the on the basis of the phase, we have seen that there is a first is the vapor power cycle and second is the gas power cycle. What is a vapor power cycle, sir? Sir, in this, phases will be like liquid, solid, gas, right? So there is a phase change, right? And in the gas power cycle, what we have seen, that gaseous phase is there, right? Gaseous phase is there. So see, we can see here there is a phase, right? Phase is there, phase is there. So, and with these two phases, we can say that there is a classification on the basis of the phases. And what is the example of the vapor power cycle? We have seen thermal power plant. Thermal power plant, this is the very biggest thing, thermal power plant. Next is what? Next we have seen that on what basis we are getting the vapor and liquid dome structure, right? So vapor on liquid dome structure. So if we have plotted these things and we have got these structure, right? So here what we have find, here is the liquid state, here is the liquid plus vapor state, here is the vapor state, and this is the liquid vapor dome. Clear? And here this line is actually known as, this line is known as saturated liquid, right? Saturated liquid, saturated liquid. And this line is known as saturated steam, right? And here is superheated steam, superheated steam. I think my cam is blocking. Let me, and this part, right? This whole part is known as superheated steam. Okay, so it is written superheated steam. Clear? So now, next we have seen what on what basis we are going to design a power plant, right? So there is a, in how we are designing the power plant, how we are designing the power plant. See here how we are going to design the power plant. So first we are selecting a boiler, right? So here there is a boiler, right? Here there is a boiler, and in this boiler we are giving the heat, we are giving the heat. And then, so in this boiler, right, a lot of water is there. So in the boiler, water is filled, right? And this water is heated, this water is heated, then it is fed to the turbine, then it is fed to the turbine. After the turbine works, right? So there is a work which has been taken out from the turbine, that is a WT, that is the WT, right? And after that we have seen there is a condenser, there is a condenser, and in this condenser there is a cooling arrangement is there, right? So in this way the heat is rejected here, heat is rejected out, and after that whatever the water we have got, we are feeding this water with the help of feed pump, pumping these water to again to the boiler, and hence this is a cyclic process in this, right? And what is the network we have seen? See, work done by turbine, work output by the turbine is WT, and work given to the turbine is feed pump is given as WP. So what is the difference between them? What is the difference between the network? Network is WT minus of WP. Clear? So why I am revising you? Because this is very much important. The revision is very much important in this subject. Okay, so there's a quick revision with that. And what is the net heat is there? So see, we are giving the heat QB and QC is rejected out. So what is the net heat? Net heat will be QB you are giving minus QC, right? So here is there Q net is equal to QB minus of QC. Now see here, what is a ranking cycle? See, we have seen these things, right? We have seen these things. So what is a ranking cycle? What is a ranking cycle? So ranking cycle is a cycle in which heat addition is at constant pressure. Clear? Heat addition is at a constant pressure. You can see this is a constant pressure, right? And heat addition is this is the heat addition. So heat addition is the at constant pressure, right? Heat addition is at a constant pressure. Now see here, this is my condenser, this is my condenser pressure, this is my condenser pressure. And see here, in this condenser pressure what we can see, this is a heat rejection, this is a heat rejection. So heat rejection is at a condenser pressure, right? And see, this is the isentropic process, right? So there is a work done by turbine at the isentropic process, right? And work you pump work is also at the isentropic process. So this is a basically ranking cycle. And what we have seen that pump work is like wp is equal to h4 minus of s3, right? And we can find this with the help of this formula. We can find it with the help of this formula. So you just have to remember that for a turbine we have wt is equal to h1 minus of h2. Clear? H1 minus of h2. For a pump we have h4 minus of h3. H4 minus of H3. Clear? And for a boiler, see, this is a boiler, this is a boiler. For a boiler, this would be H1 minus of H4. See here, H1 minus of H4. Clear? This is a condenser. This is a condenser. In condenser, the enthalpy of the steam is H2, right? And the exit enthalpy from the condenser is S3. So what would be the what would be the heat that is rejected from the condenser? That is H2 minus of H3. Clear? That is S2 minus of S3. We will be solving a lot of numericals so that everything will be get cleared. And what is the efficiency, sir? What is the efficiency? Efficiency will be net work by heat added. What is the net work, sir? Net work will be work done by turbine minus work done by pump, right? And heat added will be what? Heat added, right? Heat added, you are adding heat like this QB, right? See here. So from this formula that we have seen, that work net is a turbine minus work done by pump by QB, and based upon that we got this good formula: efficiency is equal to 1 minus QC by QB. So always remember this thing. Always remember that QC is what? Heat rejected, heat added. Even if you do not remember the formula, I am just again telling you, even if you do not remember the formula in the examination, always remember that first law is well valid for there. So just apply the first law. And what is the first law is there, sir? Efficiency is equal to 1 minus Q rejected by Q added. Always use this thing, 1 minus of heat rejected by heat added. If this is clear in your mind, always apply this concept and your formula. You do not need to remember the formula in terms of H1, H4, H3, right? And you can derive these things, right? So after that, what we have seen, next thing is what we have seen. We have seen there is a pump, right? A work pump. So WP is equal to V3 PB minus PC. What is a PB? PB is the boiler pressure and PC is the condenser pressure. PB is the boiler pressure and PC is the condenser pressure. So based upon that, these things we have seen. Next, what we have seen, there is a comparison of Rankine cycle and the Carnot cycle. From these comparison, what we have seen, that temperature is varying during the heat addition, right? Temperature is varying during the heat addition in case of a Rankine cycle. In case of a Rankine cycle, see here the temperature is varying in the heat addition, right? So, and after that, what we have seen, since the temperature, heat addition temperature is fixed, and in case of a Carnot cycle, see here. So this is the thing. This is the heat addition part for a Carnot cycle. So what we can say, that since heat addition is at a constant pressure, so hence what is the conclusion? Conclusion is that efficiency of Carnot cycle will always be greater than Rankine cycle. Efficiency of Carnot cycle will always be greater than Rankine cycle. Next, what we have seen a concept of mean temperature of heat addition, right? A concept of mean temperature of heat addition. So our aim was to increase the mean temperature of heat addition. Why, sir? Why we want to increase the mean temperature of heat addition? We have seen these things. What we have seen, that if the efficiency of Carnot cycle we are talking about 1 minus T2 by T1. Now if you talk about the Rankine cycle, 1 minus T2 by T1. So if you will increase the mean temperature of heat addition, your eventually efficiency is going to increase. So always and always, after that, what we have seen that how we can increase the efficiency of a Rankine cycle. So what is the means, like, what should be the mindset? What is the thinking? How we can actually increase the efficiency of a Rankine cycle? And this is the formula: efficiency is equal to 1 minus T2 by Tm, right? Efficiency is equal to 1 minus T2 by Tm. And see in this efficiency, this is the formula. How we can increase the efficiency? So from this equation we can see that T2 and Tm is there. So if somehow if I will increase the Tm, then again this factor will be less, and this factor will be less, then 1 minus of less factor, then efficiency will be increasing. Now see what else you can do. If you will decrease this T2, again if you will decrease this T2, then again this factor will be less, again this factor will be less, hence 1 minus of less factor is going to increase the efficiency. So this is how the efficiency is going to increase. So first way is that by increasing the mean temperature of heat addition and by decreasing the temperature of heat rejection. These things we have seen, right? These things we have seen. And after that, what we have seen, that by increasing the mean temperature of heat addition, there is a restriction. What is the restriction, sir? What is the restriction, sir? We have seen that there is a restriction in the maximum temperature, right? We cannot increase the maximum temperature as according to our wish. According to, like, we can increase the 1200 degrees Celsius or 1500 degrees Celsius or 900 degrees Celsius. We cannot do like that. That is not our home, right? That is not our father's home that we can do anything like that. So for that case, why we cannot do, sir? There is a reason. The blades of the turbine may get damaged at high temperature and not properly work, right? So this is the reason why a maximum temperature at that point is fixed. These things we have discussed those days, right? So this is the maximum temperature is fixed as 500 to 700 degrees Celsius. Rest what we have seen. So my maximum temperature is fixed. This is very much important concept. Again, I am telling you, if you haven't understood at that day, I am again explaining it. So please understand it, because this is very much important. A lot of previous year gate question has been asked from this only concept. And concept समझना बहुत जरूरी है sir. Concept समझ लेंगे सब बन जाएगा. So again, I am telling you. So see here, maximum temperature is fixed. Maximum temperature is fixed. Now what is our aim? See here. First was this, right? So first, suppose this was the cycle, right? So cycle was 1, 2, 3, 4 and 1, right? So this is my thermodynamic cycle. This is my thermodynamic cycle, and this is the Rankine cycle, right? So in this Rankine cycle, what we have seen, that mean temperature of heat addition. See here, the mean temperature of heat addition. See, the mean temperature of heat addition is very low. Mean temperature of heat addition is very low. So what I did, I increased the pressure. Suppose this pressure is 5 megapascal, I increased to 10 megapascal. So at this case, my mean temperature of heat addition will increase. Now again, if I am increasing the pressure, then again my mean temperature of heat addition will increase. But see here, when earlier I was having a Rankine cycle, then at state 2 I was having some dryness fraction. See, when I have increased the pressure, I have got the different dryness fraction, that is at 2 dash, right? Again I have increased the pressure. So when I have increasing the pressure, mean temperature of heat addition is increasing. When mean temperature of heat addition is increased, then this is 2 double dash. What is 2 double dash? At 2 double dash state, my dryness fraction is there. So see, from here we have achieved a great efficiency, because see, in this case mean temperature of heat addition is more. So if mean temperature of heat addition is more, efficiency will increase, right? Efficiency will increase. So we have got the increase in the efficiency with increasing the pressure, but at a compromise of dryness fraction. This is very much important, at a compromise of dryness fraction. So sir, हमारा dryness fraction less हो जा रहा है sir, तो dryness fraction less हो जा रहा है तो क्या problem होगा sir? If my dryness fraction will be less, then moisture content in the moisture content in that component will be more. So if moisture content in the component will be more, so that steam is actually fed to the turbine, right? That steam is actually fed to the turbine. So see here, so moisture, if moisture content will be more, then there is a lot of problem. See, if so, what we have seen, that we will get a maximum efficiency from the turbine with the sacrifice in the dryness fraction, right? So moisture will be more, and if moisture will be more, blade material suffers from tremendous erosion due to water content and particles, right? And what is the next thing? There is a corrosion occurs, right? So corrosion will occur. So now we have also seen there is a restriction in the maximum temperature and the restriction in the dryness fraction, right? So these things are there, and see, we have fixed the dryness fraction is that should be around 85%. Next concept, before going to next concept, let us see the one more thing is there, that what we have seen, axial vapor power cycle. So there is a vapor power cycle that we have studied till now, that was actually ideal in nature, right? So there is an actual vapor power cycle, where actual vapor cycle is what, like in actual case 1 and 2 is there, 1 and 2 is there, and 3 and 4 is there, but these processes are irreversible in nature. Our sole assumption is that these processes are reversible, but frankly speaking, reversible processes are not actually exist, right? So these processes are irreversible, and hence there is a change in the line, right? So for accordingly we have studied the formula, isentropic efficiency we have seen, and isentropic efficiency of a pump we have seen. So two things we have seen, isentropic efficiency of a turbine, isentropic efficiency of a pump. So these two things we have seen. Clear? Next is what? Next is we have seen the how to increase the efficiency of a Rankine cycle. So these things we have seen, mean temperature of heat addition. Next is what, sir? Next is the reheat concept. What is the concept of reheat? In this concept of reheat, see, I am increasing my pressure, right? I am increasing my pressure. pressure. Earlier this was my pressure, I am increasing my pressure, but after increasing my pressure also I am actually increasing the mean temperature of heat addition. So increasing the pressure, increasing the mean temperature of heat addition. And even if, see, if I had if the 1 to 2, like the expansion of the processes from the turbine would be like this, isentropic expansion would be there, so it would be expand like this. So at that point there would be a compromise in the dryness fraction, right? There would be very less amount of dryness fraction would be there, so moisture content will be more. So what we did, we actually placed it at the intermediate pressure. So we just expanded at an intermediate pressure. So from this intermediate pressure we increased it, and again we have means like we have added the heat till the maximum temperature, because maximum temperature is fixed. Again I have expanded, and see, at this point there is no compromise in the dryness fraction, right? So there is a heat added, heat rejected is there. Based upon that we have gone for the q added, q rejected, work done by turbine, and efficiency formulas, right? So these things we have seen in the earlier classes. So till now these things we have seen in the earlier classes. So if you have any confusion till now, then do ask with me. Otherwise I'm going to start my today's session with a very new and innovative and very good concept. I'm waiting for your reply. Just give me a reply or thumbs up so that I can proceed the next thing. I've tried to cover the previous year I mean it's like part 1 very quick, very quick. ठीक है सर, मैंने पार्ट 1 जो पढ़ाया था उसको बहुत ही जल्दी जल्दी मैंने उसको कवर कर लिया। ठीक है, ओके। चलिए तो आज का मजेदार सेशन स्टार्ट किया जाए। ठीक है, तो इतना चीज क्लियर होना बहुत जरूरी है, क्योंकि पहले जो हम पढ़ते जाते हैं उसको भूलना नहीं है, क्योंकि वही तो हमारा बेस है ना? वही तो हमारा बेस है। तो लेट अस स्टार्ट आवर न्यू टॉपिक। देयर इज अ कॉन्सेप्ट ऑफ रीजनरेशन। Concept of regeneration. See, what is the concept of regeneration? See, what was our problem? First of all, let us identify the things. So we have a boiler, right? So we have a boiler, and this boiler, from this boiler, a steam is fed to the turbine. Clear? So a steam is fed to the turbine. Now I am going very slowly, because you will not catch me if I will get very fast. Okay. So here is a boiler, and this from this boiler the steam is fed to the turbine, right? Steam is fed to the turbine. So this is a turbine, and this turbine is actually insulated. Clear? This turbine is actually insulated. Clear? So insulated turbine is there. And see here, my dear friends, see here. So from once the from here, like work done by turbine is there, right? So work is discharged from here, and after that these things like these, it goes to the condenser. Clear? Is fed to the condenser. It is fed to the condenser. Now it goes to the condenser, and there is a cooling coils with that, right? And in this cooling coil, like cold water is flowed, and after that there is a, then there is a change in the phases, right? So here's the change in the phase, and after that a feed pump is there, right? So a feed pump is there, feed pump is there, and this feed pump actually feed the water to the boiler. Clear? Feed the water to the boiler. And let me draw the TS plot side by side so that you can have a great feel what actually I am trying to say. Okay, so this is my TS plot. This is T, this is S, and in this TS plot this is my vapor, liquid vapor dome, and in this liquid vapor dome we have one pressure. This pressure is turbine, and this is the boiler pressure, and this is the condenser pressure. Clear? This is the boiler pressure, this is the condenser pressure. And see, for example, if my steam is superheated, right? If my steam is superheated, so if this is a superheated steam, so I am there is expansion of the superheated steam, right? So suppose this is 1, this is 2, After that, there is a point 3, and from this point 3 there is a pump, right? So pump helps to get it here. Pump helps to get it here. Now see here. Now see here. What are the problems here? Why we need actually the concept of regeneration? Why we need? See, my dear friends, we the concept of regeneration actually arises to increase the efficiency of Rankine cycle. Okay, we have studied the concept of reheat again to increase the efficiency of Rankine cycle. We have we have seen the concept of mean temperature of heat addition, increase the efficiency of Rankine cycle. Again, there is a concept of regeneration. Again, this is for the efficiency of the Rankine cycle we are studying, so that we can increase the efficiency of Rankine cycle. How we will going to increase Rankine efficiency in the Rankine cycle? See here, in Carnot cycle, right? In the Carnot cycle, if we say about the Carnot cycle, suppose this is my Carnot cycle, right? So suppose this is my Carnot cycle. This, this, and this, right? So this is my Carnot cycle. So see, in a Carnot cycle, heat is added to the boiler at a maximum constant pressure, right? So heat is added to the boiler at maximum constant pressure. See here, so at this maximum temperature, heat is added and it is constant, but it is not possible for case of a Rankine cycle. See here, for a case of Rankine cycle, we know that mean temperature, so we know that heat is as added like this, like this, like this, like this. So what we can say here, that see, at this point it is minimum temperature, this is the maximum temperature, this is again the change in the temperature. So there is a continuous change in the there is a continuous change in the temperature throughout the pressure line, right? So this is the problem of a Rankine cycle. Clear? So if the steam passing after one, right? See, suppose if the steam passing after one, if the steam passing after one is somehow heated and feed, see, problem is there. अगर मैं आपको बता रहा हूँ, थोड़ा ध्यान से समझे कि कार्नोट साइकिल तो ये था सर। कार्नोट साइकिल में क्या हुआ, यहां से यहां तक ही तो हीट एडेड होता है कार्नोट साइकिल में। इफिशिएंसी हम क्या जानते हैं, 1 - T2/T1, राइट। अब से देखिए, इसमें अभी इस टेम्परेचर में ही तो होता है ना, हीट एडेड तो इस टेम्परेचर में ही होता है। लेकिन अगर ये कार्नोट की बात करूं, अगर मैं रैंकाइन की बात करूं, तो 1 - of T2/Tm हमने बोला। व्हाट इज टीएम सर? टीएम ये हो गया सर मीन टेम्परेचर ऑफ हीट एडिशन। इसका एक मैं कोई मीन टेम्परेचर ले लिया जहां पर हीट एडिशन हो रहा है। अब एक बात समझिए, अगर मैं इफ एनी हाउ, अगेन इफ एनी हाउ, आई विल remove this temperature, if somehow, if some arrangement, by doing some arrangement, if I will try to make this Rankine cycle like a Carnot cycle, like a Carnot cycle, how we can make this Rankine cycle to the Carnot cycle? By adding the temperature only to this part. So what we have to do, this is the extra work, right? So for example, this is the first work that we have to do, and this is the second work we have to do. So if somehow we will give temperature to this only, then this is what, where this thing will go, so if somehow by any external agencies or by anything, if I can compensate this, then this problem will be solved. So see here what we are doing कि देखिए, अगर मैं यहाँ से 3 से 4 जो जा रहा है ना, तो 3 से 4 अगर कुछ किसी भी तरीके से 3 से 4 अगर ऐसा हो जाए, 3 to 4 कुछ ऐसा हो जाए, तो ये वाला वर्क कहाँ चला गया, ये वाला चीज कहाँ चला गया, ये वाला चीज मेरा, ये वाला वर्क जो है कोई और मेरा अगर कर दे तो बात ही बन जाएगी। कोई और ये वर्क कोई और कर दे तो बात ही बन जाएगी। तो लेट अस अंडरस्टैंड वन थिंग, व्हाट वी आर डूइंग फॉर दिस, व्हाट वी आर डूइंग, फीड पंप से जो पानी आता है, फीड पंप से जो पानी आता है वो तो यहाँ पर आता है। लेट मी रिमूव दिस थिंग। सी हियर, फीड पंप से जो है ना, अपना फीड पंप से जो है पानी कहाँ से आता है, सी हियर, यहाँ से फीड पंप से पानी आता है। अब यहाँ का टेम्परेचर क्या है सर, यहाँ पे टेम्परेचर तो लेस है, ठीक है। आप लेस टेम्परेचर को क्या कर रहे हो, सी हियर, दिस इज द लेस टेम्परेचर, राइट, सी दिस इज द स्टेट 3, दिस इज द स्टेट 3। आप जो कर रहे हो, आप क्या कर रहे हो, स्टेट 3 से आप स्टेट 4 में ले जा रहे हो, ठीक है। देखिए 1 to 2 देयर इज एक्सपेंशन, राइट, सो सपोज दिस इज माय 1 एंड दिस इज माय 2, राइट, सो 1 to 2 इज एक्सपेंशन। सो आप देखिए स्टेट 3 से आप स्टेट 4 में जब जाओगे तो क्या करना है आपको, आपको टेम्परेचर तो यहाँ पे लेस है, यहाँ पे लेस टेम्परेचर है, अगर लेस टेम्परेचर यहाँ पे आप भेजोगे तो फिर बॉयलर को ज्यादा वर्क करना पड़ेगा, है ना। इस लेस टेम्परेचर वाले वाटर को फिर से तो बॉयलर हीट करेगा ना, फिर से तो बॉयलर हीट करेगा, अगर बॉयलर फिर से हीट करेगा तो बॉयलर को ज्यादा वर्क करना पड़ा, बॉयलर को ज्यादा काम करना पड़ा। अगर मैं क्या करूं, अगर मैं क्या करूं, यहाँ से जो पानी आया, राइट, यहाँ से जो पानी आया, अगर मैं उसको किसी तरह से, यहाँ से जो पानी आया अगर उसको मैं किसी तरह से क्या करूं, उसको मैं भेज दूं टरबाइन में, उसको मैं भेज दूं टरबाइन में, क्यों भेज दूं टरबाइन में, अगर मैं सर आई कांट सी द कर्सर, प्लीज इंक्रीज साइज, ओके, अभी दिख रहा है शुभम जी, सी what I am doing, I am just feeding the water from the feed pump, water coming from the feed pump because it is have a less temperature water would be there, वाटर पार्टिकल वुड बी देयर। अभी इसको मैं क्या कर रहा हूँ, इसको मैं टरबाइन में भेज रहा हूँ, इसको मैं टरबाइन में भेज रहा हूँ। अब टरबाइन में अगर मैं भेज दूं तो टरबाइन में तो क्या हो रहा है, हीट है ना, तो ये पानी क्या हो जाएगा, हीट हो जाएगा। अगर सपोज करूं कि इसका टेम्परेचर अगर कुछ टेम्परेचर है, तो यहाँ पर सपोज करूं कि इसका टेम्परेचर अगर T3 है, ठीक है, तो यहाँ पर जा करके जो टेम्परेचर होगा T3 डैश अगर मान लो तो वो तो बड़ा होगा, T3 डैश विल बी ग्रेटर देन T3। ये चीज समझ में आया कि नहीं। अगर मैं फिर मोर हीटेड टेम्परेचर को फिर यहाँ पे फेड कर दूं तो अब बॉयलर को उतना हीट तो नहीं करना पड़ेगा, है ना, उतना हीट तो नहीं करना पड़ेगा, तो यहाँ पे काम उसका कम हो गया, है ना, काम उसका कम हो गया। सो अगर इसका काम कम हो गया, बॉयलर को काम करना कम पड़ गया, तो बॉयलर को काम करना कम पड़ गया मतलब क्या, हीट एडेड जो है ना, हीट एडेड उसको कम करना पड़ गया, समझ में आ रहा है। तो हीट एडेड कम हो गया, हीट एडेड कम हो गया, एफिशिएंसी इज इक्वल टू 1 माइनस ऑफ क्यू रिजेक्टेड बाई क्यू एडेड। सो यहाँ से हम क्या करते हैं, यहाँ से हमारा एफिशिएंसी इंक्रीज कर जाता है, ठीक है। तो ये एक कॉन्सेप्ट हो गया अपना, कॉन्सेप्ट ऑफ रीजनरेशन। लेकिन यहाँ पर प्रॉब्लम क्या है, प्रॉब्लम ये है कि सी टरबाइन में, टरबाइन इज फुल्ली पैक्ड, राइट, सो ऐसा नहीं है कि टरबाइन में हम हीटर को घुसा दें, दिस इज माय हीटर, राइट, दिस इज माय हीटर, सो ऐसा कोई पॉसिबल अरेंजमेंट नहीं होता। इट इज वेरी डिफिकल्ट to put a heater inside the turbine and then we can heat that feed pump water which is coming out from feed pump, and then we can give to the boiler. It is impossible, it is impossible, right? This concept is clear, but this in this way you cannot achieve the regeneration thing, right? तो यहां तक समझ में आ गया कि रीजनरेशन में क्या हो रहा है, ये चीज समझ में आ गया कि नहीं आ गया, टेल मी, टेल मी। तो अब क्या करते हैं ना, सी हियर, चलिए मैं आगे बढ़ रहा हूं, तो क्या करते हैं, फॉर दिस व्हाट वी डू, वी एक्चुअली मेक अ रीजनरेटिव साइकिल, लेट मी ड्रॉ इट, रीजनरेटिव साइकिल, so there is a regenerative cycle would be there, regenerative cycle, so there is a regenerative cycle. Now see regenerative cycle, what is regenerative cycle and what we do in this regenerative cycle, there is a boiler, there is a boiler, clear, this, and from this boiler you are feeding the steam to the turbine, clear, this is my turbine, and see from this turbine you are giving the, you are feeding to the condenser, right, so suppose this is my condenser, so this is my condenser, clear, there is a, and after this condenser There is a feed pump, right? Now see, here comes the twist. Here comes the twist. Now see what we do here. We actually we actually take a heater, right? We take a heater. We take a heater and see, suppose 1 kg of steam is entering. 1 kg of steam is entering into the turbine. 1 kg of steam is entering into the turbine. And what we are doing, we are bleeding out. Suppose we are bleeding out mkg of steam from here, right? Let me tell you once again. There is a 1 kg of steam which is entering, and we are bleeding out mkg of steam from that turbine. See, if we are bleeding out mkg of steam from the turbine and giving to the heater, then also my heater will serve the purpose, right? And what I will do, see here, so I have a feed pump. So water coming from the feed pump is fed to the is fed to the so water coming from the feed pump is fed to the heater, right? Heater पर feed कर दिया गया है ना. So see, पानी यहाँ से जो निकला, whatever the water that is coming out from the feed pump is fed to the heater, right? And this heater is actually given, in this heater the mkg of steam is being bled out from the turbine and it is given to the heater, right? And now this heater has actually heated this water, right? This heater has heated this water, and after that the heated water is sent to the boiler. Clear? So purpose is same. What we have seen here, the purpose is same. Clear? तो पर्पस सेम है सर. तो अपने लोग क्या करते हैं सर, हीटर ले लेते हैं. 1 kg अगर मैं यहाँ से स्टीम को फ्लो करवा रहा हूँ, mkg में अगर ब्लेड कर लेता हूँ सर, तो यहाँ पर कितना kg बच जाएगा सर, यहाँ पर 1 minus of mkg. So यहाँ पर 1 minus of mkg steam will flow from here. Clear? So 1 minus of mkg of steam will flow from here. So I think this concept is clear to you. This concept is clear to you, the concept of regenerative cycle. Hello आशुतोष. Hello आशुतोष जी, मैं पढ़ाता हूँ, प्लस पर अभी नहीं स्टार्ट किया हूँ, लेकिन मेरी फ्री क्लासेस चलती है स्ट्रेंथ ऑफ मटेरियल की, रोज 9 बजे आप कर सकते हो उस क्लास को. आशीष जी, सर स्टीम भी तो रहेगा ना हीटर में. आशीष जी, सी हियर, दिस इज माय हीटर. अब मैं क्या कर रहा हूँ, हीटर तो मेरा, हीटर क्या है, हीटर तो मेरा यहाँ पर है ना. तो स्टीम को मैं यहाँ से ला रहा हूँ, स्टीम को लाने से क्या होगा, यहाँ पर एनर्जी आ गया है ना. इस एनर्जी को मैं यूज करके इस ठंडे पानी को मैं गर्म कर लूंगा, राइट? ऐसा बोलना गलत है, बट मैं यह बोलना चाह रहा हूँ, मैं आपको सिंप्लीफाई करना चाह रहा हूँ कि क्या है कि यहाँ पे हीटर में आप एनर्जी को दिए, यहाँ से ठंडे पानी को दिए, तो यहाँ से क्या हो जाएगा, गर्म पानी निकल के आएगा. सो टेम्परेचर, इवेंचुअली यू आर इंक्रीजिंग द टेम्परेचर. क्लियर आशीष? So from here, like, temperature is increased, right? Temperature is increased. Here also temperature is increased. Here also temperature is increased, right? And then it is fed to the boiler. Here also temperature is increased and then fed to the boiler. So again, purpose is same. So I think this regenerative cycle, concept of regenerative cycle is clear to you, and hence I am telling you one more thing. 1 minute में 1 minus mkg, can you explain once? Okay, see, शुभम जी, see here, अगर 1 kg steam, if I am giving the 1 kg of steam, suppose I am giving the 1 kg of steam from the boiler, right? From the boiler you are giving the 1 kg of steam to the turbine. Clear? And from this turbine I have 1 kg of steam and I am using some amount, right? For example, like 20% of 1 kg or 10% of 1 kg, any some amount I am using the steam. I am using the steam from the turbine of some amount, and using this steam I am heating this water coming from feed pump. Clear? I am heating the water coming from feed pump so that the temperature can be increased. So I have bled out mkg. Suppose I have bled out mkg from here, then 1 kg I have given, mkg I have taken out, then 1 minus mkg will be, right, will be flowed to the condenser. Clear? And only 1 minus mkg will be left with us, right? Clear or not? ठीक है, आशीष जी का तो क्लियर होगा. शुभम जी, जस्ट टेल मी. ठीक है, क्लियर है? हम्म, क्लियर है ना? चलिए नेक्स्ट बढ़ते हैं. अपने को बहुत पढ़ना है, आज आज बहुत कुछ कंप्लीट करना है, तो आगे बढ़ते हैं. नाउ सी हियर, that case was very simple. That case was very simple. So I'm just drawing a little bit complicated case so that you will be able to understand everything. After this case आपको सब कुछ आसान लगने लगेगा. Regenerative cycle. So what is a regenerative cycle? We have seen what is regenerative cycle. We have seen. And so now suppose, now suppose, now suppose you have a, suppose you have a boiler. So this is my boiler, and from this boiler you are feeding into the turbine. Now see, from this turbine you are sending some heat, you are, after that you are, it is fed to the condenser. Clear? Suppose here is a condenser. So here is a condenser, right? And this condenser cooling water is arrangement is there, right? Suppose this is like thing is there, and so this is my condenser, and after this condenser it is fed to the feed pump. Suppose there is a feed pump one. Understand everything. I'm going slowly. So this is my boiler, my turbine, this is my condenser, this is my feed pump, first feed pump. Clear? First feed pump. From this feed pump I am getting the water discharge. Now I want to heat this water. Now I want to heat this water. Clear? So suppose what I will do, for this I will take a heater. I will take a heater. Clear? I will take a heater. I will blend out some kg of steam from here, and I will feed to this heater, right? I will feed to this heater, and when I will feed to this heater, then this water is sent to the heater. Clear? This water is sent to the heater. After that heating process will be clear. So after that heating process will be there. So let me draw like this so that you will have no confusion, right? Like this. Clear? So this is moving like this, like this, then after this, then after this, then you are feeding to the heater, and you are bleeding out some mkg of steam. After that it is fed to the boiler. But before feeding to the boiler, if I will, if somehow, if somehow again, if I will use a feed pump, again I will use a feed pump 2, right? And I am again heating the water coming from this feed pump with the heater, with the heater. And from this heater again we are giving some, we are bleeding out some mass mkg of steam, and then we are heating it. So let me just draw it, then I will explain everything. Don't worry, if you're not understanding, I'm explaining it once again. So whatever the water that is coming out from the feed pump, second feed pump, it is fed to the heater. So this is another heater, right? And the some mass of steam is bled out again from the turbine and sent to this heater. After that again the output is fed to the boiler. Here it is fed to the boiler. Why there is a need of two feed pump, why there is a need of two heater, let us understand these things and equation associated with this, because when you will understand these things you will be able to solve every problem of gate, every problem of gate, I repeat, every problem of gate and ESE. This is your fundamental. यहाँ पे अब जो समझा रहा हूं वो अच्छे से समझिए. चलिए देखिए, suppose this is my state 1. This is my state 1. Yeah, this is my state 1. Now from this state 1, let us assume this is my state 2, where you are bleeding out some m1 kg of steam. Clear? So here you are giving 1 kg of steam, and here you are bleeding out m1 kg of steam. Clear? And you are feeding this m1 kg of steam in some heater h1, some heater h1. Clear out? Now see, after that what you are doing, you are again bleeding out some, this is state 3, so you are bleeding out again some mass of steam, suppose m2 kg of steam, and feeding to the heater. So let us assume this heater to be h2. Clear? So there is a two heater h1 and h2, so you are feeding the m2 kg of steam, you are bleeding out m2 kg of steam and feeding to the heater 2. So from here what we can say that this is this, let us assume that this is state 4. So from state 4 you are feeding to the condenser, from the condenser let us assume this is state 5, and from state 5 let us assume this is state 6, from state 6 you are feeding to the heater, right? State 6 we are feeding to the heater. So after that it is moving like this, so let us assume this to be a state 7, this to be state 7, and after that this water is fed to the heat pump, again the heat pump, cold water is heated with the this h1, so this is h7 state. Let us assume this is 8th state. If this is 8th state, then this would be 9th state. Clear? 9th state. And see, we cannot, there is a problem with that, we cannot so after that what we have to do, we have to use a feed pump, right? We have to use a feed pump. The third feed pump would be there, because if we are not using pump, how we can pump this amount of water to the boiler, right? It is impossible, right? So we are using this feed pump. So this is state 9, and after that this is the state 10. This is the state 10. Clear? So this diagram is there, right? So this is the diagram. Now see, now see, if I will try to draw a I'm trying to draw a graph TS plot. Okay, so let me draw the TS plot here, and if I can draw it here, then it will be very good. Just give me some time. Suppose this is the condenser, and in this condenser you are giving the cold water. Clear? Now see, I'm just plotting the TS plot. Okay, just understand the TS plot. Very very important. Now your concept is going to clear. Now only. This is my TS plot, right? So this is my vapor dome. These things is clear to you. This is my vapor dome, and in this vapor dome, suppose, what do you have to suppose? Suppose that this is the one pressure, this is some pressure, and this is the condenser pressure. Clear? Now see, now see what is going on. There is a state 1 to state 2. Clear? So you are giving, so there is expansion, there is expansion in turbine from state 1 to state 2, right? तो अगर मैं सोचूं, अगर मैं ऐसे सोचूं कि ये स्टेट 2 स्टेट 3 स्टेट 7 नहीं होता, तो सिंपल आप क्या करते? आप सिंपल, आपका ग्राफ कैसा होता? आपका सिंपल ग्राफ होता, यहाँ से मैं टरबाइन को एक्सपैंड किया और ये यहाँ पर आ गया, है ना? ये सिंपल ग्राफ होता। लेकिन ये देखिए, ये ऐसा है नहीं अभी। अभी क्या हो गया? आपने स्टेट 2 पर m1 अमाउंट ऑफ स्टीम जो है उसको ब्लेड आउट किया। सो व्हेन यू आर ब्लेडिंग आउट m1 अमाउंट ऑफ स्टीम, then then see here what will happen. So there is some intermediate pressure, there is some intermediate pressure would be there. So what you are doing, you are bleeding out, you are bleeding out, you are bleeding out the things, right? So this is state 1, clear, this is state 1, and from this state 1 you are going to state 2, you are going to state. See this, what this is the state 2. At state 2, from 1 to 2, from state 1 to state 2, actually you are giving 1 kg of, you are giving 1 kg of water. Oh sorry, 1 kg of steam, clear, 1 kg of steam. Now see here, from 1 to 2 you are giving 1 kg of steam, and from 2, so from 2 is there, from 2 to 3, from 2 to 3 what we can see, from 2 to 3, earlier 1 to 2 1 kg of steam was there. Now from 2 to 3 we have bled out one m1 amount of steam. Then what we are left with, 2 to 3 we are left with 1 minus of m1, clear. So we are left with 1 minus of m1. So 1 minus of m1 would be there. So suppose this is now this, so suppose this is 3, and this is also at some other would be there, like this pressure line is there. So let me draw the pressure line. Now here you are giving 1 kg, from 2 to 3 m1 kg you have bled out. So what you are left with, 1 minus of m1, clear. So you are giving now 1 minus of m. So here 1 minus of m1 amount of, it is amount of steam you are giving, clear. Now from 3 to 4, see here, this is 3, see here, this is 3, 3, this is 3. So from 3 to 4, from 3 to 4 what we are doing, see, earlier there was 1, state 1 to 2 1 kg was there. Now state 2 to 3 we are taking out m1 kg. When we are taking out m1 kg, then what we are left with, 1 minus of m1. Now see, from 3 to 4 we are left with what, m1 kg तो पहले निकाल लिए थे, अभी 3 to 4 में ये m2 kg ऑफ स्टीम भी तो ब्लेड आउट कर दिए, तो हमारे पास बचा क्या, m1 भी चला गया, m1 भी हीट को ब्लेड कर दी, m1 स्टीम को भी ब्लेड कर दिए, m2 kg ऑफ स्टीम को भी ब्लेड कर दिए। तो दोनों को अगर ब्लेड कर दिया तो यहाँ पर 3 to 4 स्टेट में क्या हो गया, 1 माइनस ऑफ m1 माइनस ऑफ m2, क्लियर। So we will be left at like this, 3 to 4, 3 to 4 will be like this. Suppose this is 4, and at the state 4, at the state 4 what we are left with, we are giving 1 minus of m1 of m2, clear, 1 minus of m1 minus of m2. Now as simple as that, उसके बाद हमने क्या किया सर, उसके बाद this is 4 to, this is 4 to 5, this is 4 to 5. Now see, from 4 to 5, this is 4 to 5, condenser is there, right? And from 5 to 6, so see, this is 5 state 5. So from state 5 to state 6 you have to go. So how you can go to from 5 state to 5 6, with the help of a feed pump. So this is the feed pump, this is the feed pump, fp1, fp1 is the feed pump. So this is the state 6, this is the state 6, right? So this is the state 6. So what we can say, that it is moving like this. So this was 1 to 2, 2 to 3, 3 to 4, now 4 to 5, now 5 to 6, clear. See, this is the state 5, this is the state 6. So there is a feed pump which is required to move the to pump this state 5 uh, component to state 6, state 5 to state 6. Now see, again see, from this state 6 you are feeding this to the heater. Now see, this is the line of heater, this is the line of heater. See, this is the line of heater, right? This is the line of heater. So you are feeding the state 6, you are feeding the state 6 to this heater. See, you are feeding the state 6 to the heater. So what we will be having like this. So this is the arrow, this is the arrow. Again see, again you are left with, again you are left, because see, heater will feed and give to this point. The heater has heated the water that is going from this state 6, and then it is feeding to the feed pump. Again there is a feed pump, this feed pump is fp2 is feeding it to here, right? So let us assume this to be state 6, state 7, state 6 was there, and state 7 is the exit of heater. So this is the exit of heater. So from exit of heater it is fed to the feed pump. So again there is a feed pump fp2, and there is a state that is 8 eighth state is there. Now again there is a heater, right? See, this is a heater, h1 heater is there, and this h1 heater is heating the water coming from the state 8. And again the exit is 9, so again this is the exit, that is 9. This is the exit, that is 9. Again this exit 9 is, again it is pumped with the help of fp3 to the first pressure, and again what we are left with, we are left with the state 10. So see, this is the condition, this is the condition. Now I am just drawing this thing once again so that you will have a better clarity. Okay, so this is the graph. Let me draw like very big so that you will have, you can see, visualize the things. Suppose this is a graph, this is a vapor dome, liquid vapor dome is there, and these are the pressures. Suppose this is the pressure line, this is another pressure line, there is another pressure line, and there is a condenser. Condenser pressure is, now see here, this is the state 1, this is the state 1, clear? This is the state 1. So from this state 1 to state 2, state 1 to state 2, from state 2 to state 3, from state 3 to state 4, clear? From state 4 to state 5, state 5 to state 6, state 6. From here also it is flowing like this. So this is the direction, this is the direction, this is the direction. So this is the heater, so it is feeding. Again this is state 7, again this is state 8, again it is given to this, again the heater is heating it, again this is going to be state 9, again this is going to be state 10, and again it is given to the boiler. So see what we can see from this graph, this is the TS plot, this is the TS plot, this is the TS plot that we are getting. Now see, I have started our discussion with that if somehow I can, efficiency is equal to 1 minus of T2 by Tm, right? Tm मीन टेम्परेचर ऑफ हीट एडिशन. अगर मैं किसी तरह से मीन टेम्परेचर ऑफ हीट एडिशन को बढ़ा दूं तो क्या हो जाए, मजा हो जाए, क्योंकि एफिशिएंसी बढ़ जाएगा. एफिशिएंसी कैसे बढ़ेगा सर, यहाँ पर देखिए, मीन टेम्परेचर ऑफ हीट एडिशन बढ़ा देंगे, नहीं बढ़ गया, मीन टेम्परेचर ऑफ हीट एडिशन बढ़ गया. देखिए, नाउ दिस इज द मीन टेम्परेचर ऑफ हीट एडिशन, right? This is the mean temperature of heat addition, and this is throughout this my heat is added, throughout this my heat is added, clear? Heat is added, so my efficiency is increased. Here my efficiency is increased क्योंकि हीट एडिशन जो है हमारा ऑलमोस्ट कांस्टेंट टेम्परेचर पे हो रहा है. ठीक है, ऑलमोस्ट कांस्टेंट टेम्परेचर पे हो रहा है, क्योंकि अगर मैं ग्राफ बनाऊं पहले वाला ग्राफ कैसा बनता था, कुछ ऐसा बनता था, लाइक दिस, है ना? अगर मैं यहाँ से एक्सपेंड करूँ तो कुछ ऐसा होता था और कुछ ऐसा होता था. मीन टेम्परेचर देखिए, ये जो रीजन है, इस रीजन को मैंने छोटा कर दिया. आई हैव ट्राइड टू reduce this region, and hence the mean temperature of heat addition has increased. Mean temperature of heat addition is increased. Now tell me, if you have any problem till now to understand the concept of regeneration, then please ask me, otherwise I will derive some equations. वेलकम अमन जी, वेलकम. कुछ प्रॉब्लम है तो मुझे बताएं. रीजनरेटिव का प्रॉब्लम कुछ समझ में आया? At least give me a reply so that I can understand. आगे बढ़ूं? Feed pump cannot be in vapor dome, sir. Feed pump. Feed pump cannot be in vapor dome. No. How can it be vapor dome? सर देखिए, सर देखिए, यहाँ पर मैं क्या करता हूँ, यहाँ पर तो कंडेंसर होता है ना, यहाँ पर तो कंडेंसर होता है ना, तो कंडेंसर क्या करता है? What is the use of the condenser? Condenser actually condenses to this saturated liquid, to this saturated liquid phase, right? To this saturated liquid phase. See here the state is what? Here the state is liquid plus vapor. You cannot feed liquid plus vapor, right? So that's why we are using these state, right? So this is the feed pump. Please explain once more, I missed. देखिए एक चीज जो है, जो कॉन्सेप्ट जो है वो ये है कि बॉयलर से आपका 1 kg ऑफ स्टीम जो है वो टरबाइन में आता है, ठीक है। अब टरबाइन से आप क्या करते हो, m1 kg ऑफ स्टीम को ब्लेड आउट कर लेते हो, राइट। सो यू आर ब्लेडिंग आउट m1 kg ऑफ स्टीम एंड फीडिंग टू दिस हीटर H1. Again what you are doing, you are bleeding out m2 kg of steam and feeding to the H2. Again what you are doing, so with the help of the feed pump you are feeding to the boiler. So this is what was the concept. Now see, from here in this graph what we can see here, so this is the state 1 to 2, right? 1 to 2. So from 1 to 2 you can see that there is a 1 kg of steam is there, right? So 1 kg of steam is there. So here you are giving 1 kg of steam. Here you are giving 1 minus of m1 kg of, and here you are giving 1 minus of m1 minus 2 kg. Clear? So from here 1 minus of m1 minus of m2 kg of steam is flowing, right? 1 minus of m1 minus of m2 kg of steam is flowing. Now see at state 3, what is at state 3? At state 3 you can see m2 kg of mass is flowing, right? m2 kg of steam is flowing. So we can write like that, from state 3 m2 kg of steam is flowing, right? And see here 1 minus of m1 minus of m2 kg of steam is flowing. From here m2 kg of steam is flowing. So we can say that from here also, see at state 2, here it is m1, here it is m1. Clear? State 2 m1 is there, so we can say that m1 kg of steam is flowing. Now see, this is 1 minus of m1 minus of m2, here m2 is there. So what we can say, from here 1 minus of m1 steam is flowing, right? 1 minus of m1 steam is flowing because m2 is here, and from here 1 minus of m1 minus of m2 is there, right? So m1 minus of m1 minus of m2 plus of m2, so 1 minus of m1 kg of steam is flowing here. So from here 1 minus of m1 kg of steam is flowing, from here m1 kg of steam is flowing. This is net, this is going to be equal to 1 kg of steam. So this is the calculation. 1 kg ऑफ स्टीम कैसे घूम रहा है वो सारे जगह पर, ये आपको समझ में आ रहा होगा। 1 kg ही स्टीम कहाँ कहाँ से क्या क्या कैसे कैसे करके घूम रहा है, ठीक है। सो आई होप यू गॉट द आइडिया ऑफ द रीजनरेशन, राइट। तो शुभम जी, आई थिंक यू गॉट सम आइडिया। अगर फिर भी प्रॉब्लम है तो आई विल रिकमेंड यू टू वॉच दिस वीडियो वंस अगेन। अभी के लिए क्या आपको समझना है, फॉर दिस what you should remember is this. For a time being, what you should remember is this, that what is the work done by turbine? What is the work done by turbine? What is the work done by turbine? So work done by turbine will be like this. Clear? In this case, work done by turbine would be this. Work done by turbine would be this. Clear? So now how can I write work done by turbine? How can I write work done by turbine? So it is very easy for you, right? You can write like h1 minus of h2, right? h1 minus of h2 enthalpy. So this is the turbine, plus of h2 minus of h3 plus of h3 minus of h4, right? You can write like that, but the problem is that you cannot write like that. Why you cannot write like that? Because continuously masses are changing, so this equation is wrong, so what I need to what I need to do it here, I need to understand that there is 1 kg of mass which is flowing from state 1 to state 2. So work done by turbine is H1 minus of H2, and in this 1 kg of steam is flowing. Clear? Next, what is there? And next is H state 2 to state 3. So we can say that 1 minus of m1 kg of steam is flowing from state 2 to state 3. So there is m1. So we can say that 1 minus of m1 amount of steam is flowing, and the state is what? H2 minus of H3. H2 minus of H3. Clear? H2 minus of H3. Next, what is there? Next is this 3 state is there, and this fourth state is there. Clear? And this is the work done by turbine. So from here we can see that 1 minus of m1 minus of m2 kg of steam is flowing, right? So we can say 1 minus of m1 minus of m2 into h3 minus of h4. So this is going to be my turbine work. This is going to be my turbine work. Clear? This is going to be my turbine work. Clear or not? Turbine work is clear or not? If we talk about the Q added, how much amount of Q is added? See, very easy. Throughout this the heat is added. See, throughout this heat is added. Throughout this heat is added. So if throughout this heat is added, then what I can say, Q added is what? Q added is H1 minus of H10. Clear? Q added is H1 minus of H10. Clear? Now see, if I talk about the pump work, if we talk about the pump work, what I can write about the pump work? See, what I can write about the pump work. See here. Here 1 minus of m1 minus of m2 kg of steam is flowing. So I can write like h6 minus of h5 into this much amount of steam is flowing. So I can write 1 minus of m1 minus of m2 into h6 minus of h5. Next is what? See here. This is the state 7 and this is the state 8. From this state 7 to state 8, 1 minus of m1 kg of steam is flowing. So I can say that 1 minus of m1 into h8 minus of h7. Clear? So plus of 1 minus of m1 into h8 minus of h7. Next is what? See here. From state 8 to state 9 is there. So what we can say that state 10 to state 9 to state 10 pump is there, right? So we can say, and in this 1 kg of steam is flowing, right? So we can say this is going to be h10 minus of h9 into 1 kg of steam. Clear? So this is going to be is equal to 1 kg of steam flowing from h10 to h. This is the pump work. What was the turbine work I have written? 1 into h1 minus of h2. So I'm just writing it 1 minus of h1 minus of h2 plus 1 minus of m1 into h2 minus of h3 plus of 1 minus of m1 minus of m2 into of h3 minus of. This is the turbine work we have seen, and we have seen the heat added. Heat added is nothing but h1 minus of h. Yeah, so these three things we have seen. So once we are interested to find the efficiency of this cycle, regenerative cycle, so what we need to do? We need to do 1 minus of net work by q added. So what you can do? You can do efficiency of regenerative cycle will be 1 minus of wt minus of wp by q add. Clear? So this is the formula. यहाँ तक क्लियर है? कुछ समझ में आया यहाँ तक या नहीं आया? ठीक है, यहाँ तक समझ में आया या नहीं आया? Tell me, clear or not? Tell me. Okay, so I'm assuming that these things are clear to you. So now let us move to this. So here what we have seen, a heaters. Here what we are seeing, the heater. So this is the heater. The heater. This is the heater. Now see. Now see. If I will do the balance, heat balance, energy balance at heater 1. Suppose I am doing the energy balance at heater 1. Let me draw the heater 1. Let me draw the heater 1. Suppose there is an energy balance at heater 1. There is a heater 1. There is a heater. There is a heater 1. So in this heater 1, what was going on? This was my heater. This was my heater. Here, this was my heater. So this is heater 1. And here what is going on, you are giving m1 kg of steam, and this was state 2. Here you are giving the state 8 was there, and from here you are actually getting h9. Ninth state was there. Clear? So let me show you the figure so that you can understand. See here, this is the thing. Here, this is the thing. H1 heater is there. M1 mass of steam is bled out from here, and this is the state 9, and you are feeding the water to the state 8. Right, from the state 8 you are feeding the water. Clear? So now what we can see from here, right? What we can see from this, see here now. So now that M1 kg of steam is at state 2. Now after passing through state 9, 1 kg of steam is there, right? See here once again. See, 1 kg of steam is there. Here 1 kg of steam is there. So now 1 kg of steam is there. Clear? So now if 1 kg of steam is there, and at 8th stage you are having 1 minus of m1 kg of steam. So this is the thing that we have discussed till now. Now if I will do the heater balance, right? So I will do the energy balance for heater. If I will do the energy balance for the heater, what I will get? I will get m1 into h2. M1 into h2. Clear? M1 into h2. And see, this is entering. This is entering. Clear? This is also entering. This is also entering. And this is exit. This is going out. So what are the total in? In is m1 into state h2. Clear? What is the total in? h8 state is there, and 1 minus of m1 is there. So I can write 1 minus of m1 into state is h8, and this is equal to 1 kg into 9, that is 1 into. So this, from this relation you can find the values of m1, m2 and these things, right? Suppose if I will do the heater balance at state, this heater balance of h2, heater balance of energy balance of state, energy balance of heater 2, right? So if I will do it, let me write it here. If I will do the energy balance, at heater 2, if I will do the energy balance of heater 2, so this is my heater 2, this is my heater 2, this is my heater 2, and in this heater 2 I am feeding the m2 amount of steam, right? And this is the state 3, this is the state 3. From here, this is the state 6, you are feeding the steam, and from here the state 7 is there, that is going out. So let us see here once again. See, this is the condition, right? See, this is the condition. So what we can say here, from here m2 is there, so m2 kg is fed out at state 3, and see, this is that state 6 and this is state 7. So I can write like that. See here, once again I am telling you, this is the state 6, right? And from here, what is the amount of steam that is flowing? 1 minus of m1 minus of m2, that is flowing. So here from also 1 minus of m1 minus of m2. Now after that, you, when you are giving the 1 minus of m1 minus of m2 to this, and See here, m2 kg of steam is fed out. So what you are left with at 7 state? At 7 state you are left with 1 minus of m1 kg of steam. Clear? So 1 minus of m1 kg of steam. So what I can write here? I can write here. So there is m2 kg. So at state 6, 1 minus of m1 minus of m2 kg of steam you are feeding to it. And at state 7, at so my audio video is clear to you. Okay. So sorry for the discrepancy that happened. So let us proceed our discussion. So what I was discussing the energy balance at both the heaters. So what would be the energy balance at both the heaters? So if I will do the energy balance at heater 1 and at heater 2, then I will be getting these kind of things, right? So heater 1 and heater 2. So this is the result that we are getting. Now, now this is what is the concept of this entire vapor power cycle. So okay, fine. This was all about the concept of vapor power cycle that we have seen till now. Okay, so now we are going to discuss some of the previous year questions so that we can get a good insight about the topic. So if you could reply me, then that would be helpful for me. Everything is okay, because at all of a sudden there is a problem with the connections. Okay, fine, no problem. Let us now see some of the questions. Let us now see some of the questions and try to understand those things. There is there a network problem from your side? Asis, you cannot you see the अभी भी प्रॉब्लम हो रहा है आशीष जी? Still you are facing the problem? Now everything is my audio video is clear to you, Asis. There was some problem with my side. Okay, okay, okay. Thank you so much for replying me, because we are sitting so far and I cannot understand that whether you everything is okay or not. Okay, so thank you so much for replying. Now let us see some of the previous year questions to get good insight about the topic. So let us solve this first question of GATE 1990. Try to solve it and tell me the answer. Try to solve it and tell me the answer. So in this question, it has been told that in the Rankine cycle, when superheated steam is used, right? So when the superheated steam is used, see here, what will be the condition? For example, let me draw a TS plot. Let me draw the TS plot, and if I will draw the TS plot, so this is a liquid vapor dome, and in this there is pressure line, boiler pressure is there, and the condenser pressure. Here, condenser pressure. So now, if I will, so what is being told in this question? In a Rankine cycle, when superheated steam is used. So if I will use the superheated steam, this is the superheated steam. So if I will use the superheated steam, then what I will get? I will get like this situation. Fine, I will get like this situation. So in this situation, what I can say, this is 1 to 2, 2 to 3, 3 to 4, this is 4 to 1. Clear? Now what we can see in this Rankine cycle, when superheated steam is used, thermal efficiency will increase, right? We can easily say 1 minus of T2 by T1 is there, right? And we can say that thermal efficiency will increase. See, steam consumption decreases. What is the steam consumption? From here, work done by turbine is there. This is the work done by pump. Now see, if this is the case, we can also know efficiency is equal to work network minus of Q added. So from here we can say that what is the steam consumption rate? What is the steam consumption rate? Steam consumption. So what is the steam consumption? That is 3600 by network. So see, if my efficiency is increasing, my network is increasing. My network is increasing. That means network is increasing. That means it is going to increase. So definitely steam consumption will decrease. Clear? So steam consumption, since steam consumption will decrease, steam consumption decreases. Clear? So steam consumption decrease. So now steam dryness fraction after expansion increases. See, if you would have expanded, from here, then this would be the dryness fraction. Now if you have expanded from superheated part, this is my dryness fraction. So see here, dryness fraction is more. Clear? So we can say steam dryness factor after expansion is increases. So this is also true, this is also true, this is also true. These three are true, so hence option D is correct. All of the above. Clear? Try to solve this question. In a Rankine cycle, heat is added. In a Rankine cycle, heat is added. In a Rankine cycle, heat is added at what? See, okay, let me try to solve it. See what is being told. Option D, reversible at constant. See here. So what we can see here is that in Rankine cycle heat is added. So let me draw a Rankine cycle, and this is my Rankine cycle. For this is TS plot is there, and in this TS plot is the vapor dome. This is the vapor dome. This is the constant pressure line. This is the constant pressure line, and here this is what is expansion of the turbine. So 1 to 2 is there, 2 to 3 is there from here, and from here 3 to 4 is there. Clear? So now what we can see here, that throughout this the heat is added, heat is added. And see, this heat is added, and what is this? This is the constant pressure line, constant pressure line. We have seen these things, right? So there is a heat addition which is reversible, so we can say that reversibly heat is added at constant pressure, heat is added as constant pressure. Now see, now try to solve this question. For a given set of operating pressure limit of a Rankine cycle, the highest efficiency occurs for. See, for this type of question, I am just again telling you, always and always keep in your mind that efficiency of regenerative regenerative cycle is greater than efficiency of reheat cycle is greater than efficiency of superheated superheated cycle is greater than efficiency of saturated cycle. Always remember this thing. If you will remember this thing, then you will solve the problem. And these things we have seen, right? These things we have seen earlier. There was a saturated, then what we do, we went to the superheated. And when we are doing the superheated steam, when we are giving the superheated steam to the turbine from the boiler, and then we are expanding, we are getting the more efficiency. Again we want to increase the efficiency, so we increase the efficiency with the help of reheat by increasing the mean temperature of heat addition. Again what we did, we use the regenerative process to increase the efficiency. Sorry, so this is the chart, so this is the chart that you have to clear. So if you will remember these things, first is this, second is this, third is this, and fourth is this. Clear? So there would be for a given set of operating pressure limit for a Rankine cycle, highest efficiency occurs in regenerative cycle. Highest efficiency will occur in regenerative cycle. Now try to solve this question. Try to solve this question. Is it true or false? Tell me. It will be true or false. Tell me. Okay, see here. What is being told in this question? Consider a Rankine cycle with superheat. Okay, if the maximum pressure in the cycle is increased without changing the maximum temperature. So let me draw this. Right, so this is a liquid vapor dome. And in this liquid vapor dome, what is being told, that maximum by changing the maximum temperature, what you are doing, you, if the maximum pressure in the cycle is increased, so you are increasing the maximum pressure, right? So you are increasing the maximum pressure. So suppose there is a one another pressure is this, so there is another pressure is this, there is another pressure is like this. Clear? So if this is the maximum temperature, this is the maximum temperature, this is the maximum temperature. Now if you will expand, suppose this is my condenser pressure, clear? Now if you will expand it, see, if you will expand it from here, then you will get like this, right? If you will expand it like here, you will get like this. And even you will expand it like this, and then you will get like this. So what you can see from here, that if your maximum temperature is fixed, and if you are changing the pressure, you are increasing the pressure, then what you are getting, your dryness fraction is going to decrease, right? Dryness fraction is going to decrease. So dryness fraction is going to decrease. See, these things we have seen in this case. See here, right? See here, these things we have seen, right? So when you are increasing the pressure, keeping the constant temperature fixed, so what you are getting, a change in the dryness fraction. So dryness fraction would be decreasing. Dryness fraction would be decreasing. Clear? So we can say that dryness fraction will decrease, and here it is written in increase, so it is false. Yeah. Next, now try to solve this question. Try to solve this question. GATE 1997 problem is there. Try to solve this question. Try to solve this question. GATE 1997 problem is there. Will you able to solve it, or should I solve it? Would you able to solve it, or should I solve it? Let me know. Let me know. See, A. You're telling A. No, Asis, no. Let us see. Let us see. Let us see. Let us see, and then you will be able to understand. So suppose that consider an actual regenerative ranking cycle with open feed water heater. So suppose there is an open feed water heater, is there, right? This is a heater. Suppose this is my heater, and in this heater what is being told that for each kg of steam entering the turbine, m kg of steam with a specific enthalpy h1 is bled from the turbine. Suppose what is being written here, how you have told A, how you have told A, Asis, how you have told A, you should have at least thought about the things. Just now I have told you these things, right? Here, just now I have told you the energy balance at heater 1 and heater 2, right? So it is like you should not do like that, but see here, I'm explaining once again. So if this is my heater, right? So suppose this is a this is my turbine, right? So from this turbine what you are doing, you are bleeding out some mass, right? So you are bleeding out some mass, right? So what is being told, m kg of steam with a specific enthalpy h1, right? So you are bleeding out m1 sorry, you are bleeding out m kg of steam, mkg of steam with the enthalpy h1. Clear? With the enthalpy h1. Now see what is being told here. From this you are using the condenser, right? Suppose you are using the condenser is there, and from this condenser what you are using, you are feeding this thing to the heater, right? You are feeding this thing to the heater. See here, from the condenser to the pump and then pump to the heater. Clear? So we can draw like this. There would be a pump, there would be a pump, and with this pump you are feeding to the heater. Here we are feeding to the heater. So what is being written here, that h1 is blade from turbine, and the specific enthalpy of liquid water. So from here liquid water is entering, from here liquid water is entering, so specific enthalpy of liquid water entering the heater is h2. So here is the specific enthalpy of water, that is liquid water entering to the heater, is h2. So and then h3 is the specific enthalpy of saturated liquid leaving the heater. Suppose from here the h3 amount of heater is there. So suppose here m1 kg of steam is entering, here 1 kg of steam is entering, and from here 1 minus of m1 kg of steam is entering. So if I will do the energy balance, and I will do the energy balance, what what I'm getting, see here, I'm getting m into h1 plus h2 into 1 minus m1 is equal to h3. So let me write things. So if I will do the when I will do the energy balance, I will have m into h1 plus 1 minus m1 into h2. and this is equal to 1 into H3. So now if you will rearrange it, so see, you will, when you will rearrange it, you will get as mH1 plus of H2 minus of M1 H2 is equal to H3. Clear? So when I will do it, it will get as H2 minus of M H2 minus. From here what you will get, you will get option. From here what you will get, you will get option C. Clear? Is this clear to you? Is this clear to you or not? Just let me know. Okay. So now, so now, now try to solve this question. GATE 2002. Now try to solve this question. 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 See here, in this question, what is being told, that efficiency of a superheat Rankine cycle is higher than the simple Rankine cycle because. So see how you can. Is it B, sir? Okay. Yes, sir. It is B. It is B. But how it is B, sir? Let us understand. Efficiency of superheat Rankine cycle. So right. So suppose this is the Rankine cycle, and in this is the pressure line is there. Clear? This is the TS plot is there. Here superheat Rankine cycle. So suppose this is the superheat Rankine cycle and this is saturated Rankine cycle. So from here what we can say, that when we are having the superheat, in this case Tm, mean temperature of heat addition, is higher. So we say that mean temperature of heat addition is higher. Clear? Now see, again there is another GATE question, GATE 2003. What is being asked in this question? In Rankine cycle, regeneration results in higher efficiency because. Why regeneration occurs? Regeneration results in higher efficiency. So we have seen that regeneration occurs higher efficiency because average temperature of heat addition in this boiler has increased. Right. So this is the answer. Clear or not? These things are getting clear to you or not? Now, Now this is the GATE 2004 problem. This is the GATE 2004 problem. Let us try to analyze this problem. Okay? Let us try to analyze this problem. Don't solve it. I am solving it because if you will solve it, you will take a lot of time. Let me solve it, and you just try to understand what is going on. Clear? What is going on? So see here. It is written that consider a steam power plant using a reheat cycle. Clear? So there is a reheat cycle. So just to fix that, there is a reheat cycle. Now consider a steam power plant using a reheat cycle as shown. Steam leaves the boiler and enters the turbine at 4 MPa and 350 degrees Celsius. Right? So 4 MPa and 350 degrees Celsius. So see here, there is a 4. So there is a H3 which is entering the turbine, and this is having a 4 MPa. 4 MPa, right? So 4 MPa is the turbine at which the upper pressure is 4 MPa, which is given, and see the lower pressure is given as 400 kilopascal. Clear? 400 kilopascal. So let me draw the figure first. Let me draw the figure first. So this is my vapor dome here, and let us assume this to be a pressure line pressure line of 4 megapascal. Clear? 4 megapascal. And see, there is another pressure line of 400 kilopascal. Clear? So there is another pressure line of 400 kilopascal. So what we can see here, so what we can see here, so there is a 400 megapascal, there is a 400 kilopascal. So there is another line of 400. Okay. These are the two constant pressure line, right? So let me write here so that you will not have it. 400 kilopascal is there, 4 megapascal is there. Clear? Now see. Now see it here. So what is being told in this question? So after expansion in the turbine to 400 kilopascal, and then steam is reheated to 350 degrees Celsius. So there is a, this is the intermediate pressure which is given, and then they is expanded to the low pressure turbine of 10 kilopascal. So see here. See here what is given in the, this pressure is given as 400 kilopascal, and this pressure is given as 10 kilo, right? 10 kilopascal. This is the condenser pressure. This is the condenser pressure. This is a boiler pressure. So what is being told in this question, that there is a maximum temperature that is 350 degree, that is fixed, right? So there is a 350 degrees Celsius here. So this is the 350 degrees Celsius temperature. So now if you will do it, what you will get is this. This temperature is fixed. This temperature is fixed. Clear? So see. So in this question, it is told that steam leaves the boiler and enters the turbine at 4 MPa and 350 degrees Celsius. So see, 4 MPa and 350 degrees Celsius. Clear? 4 MPa and 350 degrees Celsius. And from here, it has been told that it is expanded. The steam is expanded. Expansion is there up to intermediate pressure, that is 400 kilopascal. So there is an intermediate pressure is there, that is 400 kilopascal. Clear? So this is 400 kilopascal. Now see, after that, the steam is reheated. Again, this steam is reheated and then expanded in the low pressure turbine to 10 kilopascal. See here, again it is reheated. So reheated to the same temperature. So this is 350 degrees Celsius temperature. This is the T. This is the TS plot. T. This is S. And here this is the pressure. This is state 1 and this is state 2. So suppose, so in this question it has been given this is state to be a state 3, H3 is given, right? See, this is the H3 which is given. So what I can write here to be H3. So after reheating, what is being told, that you have to expand it. So you will, suppose you are expanding it like that, right? So you are expanding it up to some pressure. Okay, clear? So this is the thing that we are getting, and this pressure is 10 kilo Pascal. So now this is the state 3, this is the state 3, and this is the state 4, this is the state 4, right? So I can write this state 3, the state 4, and this is the state 5. Again reheat is there, so reheat is state 5, and the state 5, and this is the state 6, the state 6. Clear? Now see here, so when these are the conditions, so what we can say, that after that 6, from state 6 we can say that from here we the pump is feeding to the this part, right? So see, this is the, so this is the 3, this is the 1, and this is the 2, this is 3, 4, 5, 6, right? From here the things are like this. So in this question it has been told, so this is the reheat problem, this is the reheat problem, right? And in this question it has been told to find the thermal efficiency. How you can find the thermal efficiency? How you can find the thermal efficiency? So thermal efficiency you can find by work done by turbine. Work done by turbine is equal to heat added by the turbine, heat added to this right? So see, what is the work done by turbine? How you can find the work done by turbine? This is the work done by turbine, work T1 and work T2, right? So what I can write from here, that WT net work done by turbine is H3 minus of H3 minus of H4 plus of H5 minus of H. So H5. Now see in this question it has been written, see here, 3095 H3 is given. Clear? H3 is given. Now see here, 26095 H4 is given. So H3 minus H4, this is clear to you. H3 is 3095, H4 is 2609. So I can write as here, work done by turbine is 3095 minus of 2. Next is what? H5 minus of H6. Let us see whether it is given or not. H5, see here, this is H5. H5 is given as 3170. H6, this is also given 2165. Just we have to substitute these things. 3170 minus of 2165, and then you will be getting work done by turbine is equal to 1492 kilojoule per kg. Kilojoule. Clear? Now see, in this question it has been told to find the thermal efficiency, neglecting the pump work, right? So you can neglect the pump work, what is the Q added, what is the heat added? Can you tell me what is the heat added? See here, in this case, what is the heat added? Heat added is this. This is the heat added, right? This is the heat added. So what I can write like that, heat added is this. So what is Q added? What is Q added? Q added is nothing but H3 minus of, right? H3 minus of H2. What is H2? What is H2? So in this question, H2 is not given, right? So in this question, H2 is not given. So what we are going to take, see here, in this question, H2 is not given. So this is the state 2, this is the state 2, and this is state 1. The state 1 enthalpy is given as 29.3. What is the state 1 and state 2? Let us analyze in this question. See, this is the state 1 and this is the state 2. So in this question it has been told to neglect the pump work, right? So since pump work will be neglected, this is equal to 0. So what I can write as H2 is equal to H1, right? So H2 is equal to H1. So you can say that heat added is this, from 2 to 3 heat is added, and from 4 to 5 also heat. Clear? So heat added can be written as H3 minus of H2 plus of H5 minus of H. Now see, since work done by pump can be neglected, so H2 is equal to H1. So I can write as H3 minus of H1 plus of H5 minus of H4. What is H5 minus of H4? So see, this is the H5 minus of H4. Now I can put the values. H3, we know H3. See, this is the H3, 3095. What is H1? What is H1? So H1 is given as, see here, in this question it is given, H1 is 29.3. So minus of 29. Clear? Now if I will add it, H5 minus of H4. What is H5? What is H5? See here, H5 is given as 3170. So I can write as 317. What is H4? H4 is 2609. So 2609. Now if you will do it, you will get as Q added. Q added is actually 3626.7 kilojoule per. What is the efficiency? What is the efficiency? Efficiency will be work done by turbine minus work done by pump by Q added. Now we know that we have to neglect this thing, right? We have to neglect this thing. Then our value will be, efficiency will be work done by turbine by Q added. How H2 is equal to H1? Okay, see here. How H2 is equal to H1? What is the pump work? What is the pump work? See, what is the pump work? What is the pump work? Can you tell me what is the pump work, Ashish? What is pump work in terms of H2 and H1? See here in this case. See, pump work is H4 minus H3. It means what? See here, this is the H4 and this is the H3, right? This is the pump work. So what I can say from here, I say that, so what we can say that this is going to be is equal to H2 minus of H1. So pump work will be H2 minus of H1. And see, in this question it has been told to neglect the pump work, right? See here, to neglect the pump work. Pump can be so neglecting the pump work, right? So neglecting the pump work. So when you are neglecting the pump work, it means you are making it zero. So H2 is going to be is equal to H1. Clear? It is going to be equal to zero. So from here, what you can say that efficiency is equal to work done by turbine by Q added. And what is the efficiency? You have got work done by turbine is 1492. So you can write as 1492 kilojoule per kg. And what is the Q added? What is the Q added? Heat added is given as C. Heat added is given as, you have found heat added as this 3626.7. 3626.7. So we will just write here 3626.7, 3626.7 kilojoule per kg, and when you will simplify you will get as 0.41, which is nothing but 41. Clear or not? Is this clear to you? So answer is going to be B. Now everything is clear. Now is it clear to you or not clear? Just let me know so that I can proceed next question. Okay. Okay. So now let us see next question. Now let us see next question. See, in this question, what is being written? Consider, same question is there. Next is there enthalpy at the pump discharge. That is, they are asking about the H. They are asking about the H2. See, see here. We have just now seen H2 is equal to H1. But see, we know that this H2 will be greater. This H2 will be greater than H1. So we know that H2 should be greater than H1 in actual practice. Right, in actual practice. And now see, H1 is what is given as H1. See, the H1 given is 29.3. So what we can say that H1 is 29.3. H1 is 29.3. So H2 should be greater than H1. So H2 should be greater than H1. That is, H2 should be greater than 29.3. So just if we are knowing this thing, H2 should be greater than 29.3, then this option from here is 33. The option is the answer. Without calculating, without doing the proper calculation, only you can get the answer. Clear? This problem is clear to you? So if this problem is clear to you, now try to solve this problem. Try to solve this problem. 33.33. Yes, Asis, yes. You don't need to calculate even. Even you don't need to calculate those things. Yes. Or by pump work we can also proceed. Yes, 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 Asis. Or by pump work we can also proceed. So tell me this answer of this question. Okay, see here in this question, in this previous GATE question, what is being told? Determine the correctness or otherwise assertion. Assertion is given as and reason is given. So what is the assertion that has been given? In a power plant working on a Rankine cycle, the regenerative feed water heating improves the efficiency of a turbine, steam turbine. These things we have seen that if we are using a regenerative feed water, then efficiency will increase, right? Efficiency will increase. We have seen that when you will using the regenerative feed water, efficiency will increase, right? Efficiency will increase. Now see, what is the reason they have given? The regenerative feed water heating raises the average temperature of heat addition in the Rankine cycle. Yes, see, the concept of efficiency is 1 minus of T2 by Tm. So how, if your efficiency is increasing, how the efficiency are increasing? Actually, when you are increasing the mean temperature of heat addition. So this is also true, this is also true. So both are true, and C, we can say that both A and R are true, and R is the correct expressions of A. Clear? Clear. Now now let us try to solve this question. GATE 2006 question is there. Try to solve this question. Try to solve this question and tell me the answer. See, okay, let me draw the things, okay, so that so see here you will have require a concept of Rankine cycle. So see, there is a Rankine cycle, and in this Rankine cycle we have a PV plot. We have a PV plot. There is a PV plot, and in this PV plot we have a this. So if we will do this, so what we can say, this is the pressure, this is the constant pressure line, the constant pressure line. In this constant pressure line, from here to here, right, from here to here, we are getting like this. Okay, this. So this is 1 2 2 2 2 3 3 2. Clear? This is the graph of the Rankine cycle, and in this Rankine cycle, this is the heat added. This is the heat added. Clear? So this is the heat added. Clear? Heat added is Q added is there. Now Q rejected is what? This is the Q rejected. The Q rejected. Q rejected. This is the Q rejected. And see, this is the Rankine cycle. Next, what is there? Next, what is there? This is the Otto cycle. Let me draw the Otto cycle. Let me draw the Otto cycle. So in case of Otto cycle, what will be there? I will draw the PV plot. If I will draw the PV plot, then I will get like this. So from here to this, there is a, what is there? There is a entropy, constant entropy process is there. So for example, 1 to 2 is the constant volume heat addition, right? So 1 to 2 is the constant volume heat addition. There is again entropy is constant, and again there is a volume constant, and then again there is a entropy constant. This is what is the Otto cycle. And see, from here we can see that entropy is equal to constant here, entropy is equal to constant here, and 1 to 2 is your heat addition, that is the volume is equal to heat addition. So here we can say this is the heat addition. This is heat addition, Q added, and from here this is Q rejected. From here this is Q rejected. Clear? From here this is Q rejected. So now what we can see, this is the PV plot of a Otto cycle, right? Now if we draw the plot of a, we draw the plot of a, we draw the plot of a Carnot cycle. Okay, so let us draw the plot of a Carnot cycle. So what will be in the case of Carnot cycle? There is a P and there is a V. There is a P and there is a, yeah, there is a P and there is a V. So in this case, what will be happening? So there is a constant temperature I line is there. Again, there is a constant temperature line is there. Again, there is a entropy line is there. Again, there is a entropy line is there. So this kind of thing is there. And here, this is suppose the 1 to 2. So 1 to 2 process is there. This is the graph, right? So there is entropy is equal to constant. Here then is a temperature is equal to constant. Here again there is a entropy is equal to constant, right? And here the, this is the temperature is equal to constant. So these 1 2 2 3 4 is there. Clear? 1 2 3 4 is there. So now if I will do this, right, so where is the heat added? Where is the heat added? This is the heat, right? Q added, Q added. And see, this is the Q rejected, Q rejected. Clear, this is the Q rejected. See, this is the Carnot cycle. Now, what would be the diesel cycle? Let me draw the diesel cycle. Let me draw the diesel. Let me draw the diesel cycle. This is the PV plot. This is a PV plot. So diesel cycle is what, like, this is the entropy, constant entropy process would be there. Heat added at this, right? Yes, right. So suppose this is 1 to 2 to 3 to 4 to 5, right? So here is a Q added here, here is a Q added, here is a Q rejected. Clear. Now if you talk about the Brayton cycle, if you talk about the Brayton cycle, for a Brayton cycle, this is the PV plot, this is the PV plot. This is like this. Okay. So here Q added would be there. Q added would be there. Let me draw the lines. 1 to 2 processes there. This is 1 to 2 process. This is 3 2 to 3 process. 3 to 4 processes there. So here is a Q added and here is a Q rejected. Here is a Q. Now see, if you will see these things, what is being asked in this question. So there is a 4 cycles: Rankine cycle, Otto cycle, Carnot cycle, diesel cycle, and Brayton cycle. So I have drawn everything for your convenience, and when you will see these things, Q rejected. So see this thing. Pressure is equal to constant. Pressure is equal to constant. Pressure is equal to constant. In which Brayton cycle? See, group 2 shows different heat removal process. So this is the heat removal, Q rejected, and this is the Q added. So the Q added. So you just have to see pressure is equal to constant and pressure is equal to constant. So at constant pressure, in which of the things heat is added and heat is rejected. So from here, when you will see it, you will get as in Rankine cycle. See, in Rankine cycle, constant pressure heat. See, constant pressure heat added is there and constant pressure heat rejected is there. Clear. So we can say that this is, we can say that PS1. I can write as PS1. Now search in which of the option PS1 is there. PS5 is there, R2 3 is there. Okay, PS1 is there, right? So here PS1 is there. Clear. Here also PS1 is there, here also PS1 is there, here also PS1 is there. Okay, so fine, ठीक है, कोई दिक्कत नहीं. Oh, this is the PS1. Now see, next is temperature is equal to constant. When temperature is constant, again temperature is constant. So at constant temperature, heat is added and heat is rejected. Heat is added and heat is rejected. So what we can see here like this, let me say. So see, at constant temperature, heat is added and heat is rejected. See, in the Carnot cycle, we can say that at constant temperature, heat is added and heat is rejected. So constant temperature, that is R, constant temperature, that is U. In this case is the Carnot cycle. So RU3. Clear. Next is what? See, pressure is equal to constant, and the pressure is equal to, so from here only you can say that RU3 is in this option, right? RU3 is in this option, RU3 is in this option. Okay, so fine, so we can say that this option and this option will not be there. So only option A and option B would be there. Clear. Now see, this is PS1. So PS1 is there, RU3 is there. Now let us see PS5. Let us see PS5. What is P? P is pressure is equal to constant. So constant pressure heat addition. What is S? Constant pressure heat rejection is there. So next is, if this is the case, then Brayton cycle. Let us see. Let us see Brayton. So there is a constant pressure. Constant pressure. So pressure is equal to constant, right? So here also pressure is equal to constant. Pressure is equal to, pressures are constant. Heat addition and heat rejection are here. So what is my option? My option is this. The option. Clear. This is my option. So things are clear to you. Things are clear to you. Now, can you tell me the answer? for this question? Can you tell me the answer for this question? Everything is clear to you till now? ठीक है, समझ में आ रहा है? No, Ashish. This is only the vapor power cycle. After that vapor power cycle, some at some other day I will take the Britain. Tell you the Britain cycle. After that, that is gas turbine, right? अभी वेपर पावर साइकिल पढ़ रहे हैं. ठीक है. जस्ट मैंने आपको ग्राफ बता दिया, because graph is very much important. From this graph only you will be able to understand the thing, right? Try to tell me this answer. Tell me the answer of this question. Hmm? Should I solve it? See. Okay, okay. Let me try. Let me tell you the answer. See here in this question, what is being told? Which combination of the following statement is correct? Incorporation of heater, reheater in a steam power plant. So when you are incorporating the reheater, what is happening? What is happening? See, always increase in the thermal efficiency of a plant. Okay. So when you are incorporating the heater, it does not mean so it does not mean that, see, always increase the dryness fraction of steam at the condenser inlet. So this is for sure, because at the condenser inlet my dryness fraction will increase. This is true. Always increase the mean temperature of heat addition. Always increase the specific work output. See, we cannot say always it is going to increase. See, it is only being told that you are using a reheater. Using the reheater does not mean that you are using the regeneration process, right? You are not using the regeneration process properly. If the regeneration would be told, then only you can say. And hence, so what we can say, that if reheater will be used, then dryness fraction will be increased. And the if dryness fraction will increase, if reheater used, so turbine work will be more. So turbine work will be more, then steam consumption rate, steam consumption, the steam consumption is what? 3600 by network. So if this network is going to be decreased, so this is going to be increased. So always increase in the specific work output, and always increase in the dryness fraction. This is the correct answer. Okay. So now let us see the another problem. Let us see the another problem. Yes. Now try to find the question. Try to find the answer of this question. This question is very easy. Easy problem is there. You can easily find the answer. Just have an attempt, and then I will explain this question. Then I will explain this question. See in this question, see. I'm trying. See, this is the heater, right? So this is my heater. In this question, this is the heater, And from here, the thermal power plant operates on a regenerative cycle with a single open feed water heater, as shown in the figure. For a state point shown, the specific enthalpy H1 is given as 2800. So this is the H1. This is 2800. Clear? And the H2, that is 200 kilojoule per kg. No assist, that is wrong. No assist, that is wrong. So H1 is given as H1 is given as 2800. And see what is the H2? H2 is given as 200 kilojoule. So now what I can write here, so if I will write the heater, right? So let me draw the heater. This is the heater. In this heater, uh 2800 kilojoule per kg enthalpy is entering, right? It is entering, and the bleed to the feed water heater is 20% of the boiler. 20% of the boiler. So what I want to say, suppose if 1 kg is flowing through it, so 20% is bleed, so 0.2 kg is bleed, and 0.8 kg is going this side. Clear? So what I can say here, this is 0.2 kg is going here, right? Now see, this is the H2, this is the H2. So H2 is there, right? So this is the H2, 2 point is there, and this is zero point 0.8 kg is entering, 0.8 kg is entering. So and it is going out. So this is the 3 state, right? So this is the 3 state. So what I can write here as bleed means air. ब्लीड मीन्स सर, ब्लीड मीन्स व्हाट, ब्लीड जो है ना, ब्लीड बोलने का मतलब यह होता है शुभम जी कि मैं वहां से कुछ एयर को निकाल, कुछ स्टीम को निकाल लेता हूँ, निकालने को बोलते हैं ब्लीडिंग, राइट? वैसे कि आप समझ लीजिए कि जैसे आपका खून जब होता है ना, जब आपको मैं चुभा दूं, कुछ खून चुभा दूं, तो आप क्या बोलते हो कि ब्लड ब्लीडिंग हो रहा है ना, खून बह रहा है, ब्लड इज ब्लीडिंग। सो उसी तरह से क्या होता है, जब टरबाइन में आप स्टीम को निकालते हैं तो स्टीम भी बहता है, और उस बहने को हम कहते हैं ब्लीडिंग ऑफ स्टीम, राइट? क्लियर शुभम जी? So now this is zero point 0.8 kg, right? And this is 1 kg, and this is 1 kg. So this is state 3. So what I write, this is the state 1, this is the state 1, and this is the 0. 0.8. So what I can write here as, see, this is the input, this is entering, so this is entering, this is entering, and this is out. So what I can write here, is 0.2 into state 1, 0.2 into state 1 plus zero point 0.8 into state 3. This is actually going on with 0.2 into state 2, this is state 2, and 1 into state 3, 1 into state 3. So from here you know that H1, what is H1? H1 is 2800. So 0.2 into 2800 plus 0.8 into H2. What is H2? What is H2? So H2 is C, 200. So we can write 200 is equal to 1 into H3. So from here you can calculate H3 is equal to 7. Clear? चीजें समझ में आ रही है आपको? थक तो नहीं गए? थक गए तो फिर मैं छोड़ देता हूँ. If you have exhausted, then I will leave. Then at some other day I will do the part 3. No problem. समझ में आ रहा है सारा चीज? Are you understanding? कोई प्रॉब्लम यहाँ तक किसी भी तरीके का? Any type of problem? Okay. Okay. ओके ठीक है. तो चलिए एक और क्वेश्चन कर लेते हैं और फिर हम लोग जो है ना, या ठीक है चलिए कोई बात नहीं है। तो फिर बाद बाकी का क्वेश्चंस जो है, जैसे कि सपोज करें दिस इज फॉर वन क्वेश्चन वाज देयर, टू, थ्री, फोर, फाइव, सिक्स, सेवन, एट, नाइन, टेन, 11। सो 11 क्वेश्चंस वाज देयर। सो चलिए कोई बात नहीं है, मैं नेक्स्ट क्लास में ही करूंगा। एक और पार्ट बना लेता हूँ, पार्ट 3। इन दिस पार्ट 3 ओनली दिस 11 और 12 और 15 क्वेश्चंस देयर, और उन क्वेश्चंस को हम डिस्कस करेंगे अच्छी तरीके से। ठीक है, कोई बात नहीं है, वी विल डू फॉर अ पार्ट 3। जल्दी मैं बनाऊंगा, होपफुली कल ही बना देता हूँ। और टिल नाउ इफ यू हैव एनी डाउट देन प्लीज आस्क विद मी। ओके, कुछ भी डाउट है या कोई भी टॉपिक जो मैं अभी पढ़ाया हूँ उसको फिर से समझना है तो वो भी मुझे बता दें। If you have any doubt and if you have any problem in learning the topic, then again you can tell me and I will try to explain you these things. Hmm. And if you are planning for a sub plus subscription, then you should use my code SIRVK, SIRVK, where you will get a 10% off. As well as I will help you throughout your preparation. I will help you throughout your preparations. Okay. And 9 बजे मेरी स्ट्रेंथ ऑफ मटेरियल की क्लास होती है ऐप पर। जो नहीं करते वो अटेंड कर लें। और 8:45 को तो आपको पता ही होगा कि मैन्युफैक्चरिंग की क्लास होती है जिसमें मैं कास्टिंग कर रहा हूँ। ठीक है। सो एनी डाउट सर, ये वेपर कंप्रेशन साइकिल का क्या क्या साइकिल का? ओके, वेपर कंप्रेशन साइकिल का एक क्लास लेने बोल रहे हैं। ओके, ठीक है, मैं देखता हूँ। I'll try. A lot of videos and a lot of subjects are there, so काफ़ी ज़्यादा वर्कलोड हमारे पे भी हो जाता है। सो आई विल ट्राई माई बेस्ट। सर नेक्स्ट क्लास में सिर्फ एक बार रिवीजन करवा दीजिएगा। यस, बिल्कुल बिल्कुल बिल्कुल। आज मैं ऐसे बहुत क्विक रिवीजन करवा दिया था, तो क्या ये एनफ था या स्लो स्पीड में जाऊं? टेल मी। नेक्स्ट क्लास में मैं डेफिनेटली करूंगा। नेक्स्ट क्लास में मैं डेफिनेटली स्लो जाऊंगा और रिवीजन करवा दूंगा, क्विक रिवीजन करवा दूंगा। और फिर क्वेश्चंस को सॉल्व करेंगे। एनी अदर इश्यूज? एनी अदर इश्यूज? कुछ और इश्यूज हैं? एनीथिंग? और आप जो हैं अपने फ्रेंड सर्कल में शेयर कर सकते हैं इस वीडियोस को। एंड इफ एनीवन इज प्लानिंग फॉर अ प्लस सब्सक्रिप्शन, लेट देम नो अबाउट मी एंड my code is SIRVK, and if you will use my code then you will get a 10% discount. So everything is okay. So should I end the session? You have any doubt? Do you have any doubt? Any doubt? कोई भी डाउट है क्या? डाउट बचना नहीं चाहिए क्लास क्लास के एंड में। ठीक है शुभम जी, मैं क्विक रिवीजन करवा दूंगा। क्विक रिवीजन, श्योर श्योर श्योर। देखता हूँ, आई विल ट्राई। अगर पॉसिबल हो तो कल करूँ या फिर नेक्स्ट कभी भी स्केड्यूल कर सकता हूँ। वेन एवर आई विल डू इट यू विल बी अपडेटेड। You will be updated. Stay tuned with me. Always and follow me at Unacademy learning app. I'm doing the strength of material there. Subham, you can also attend my strength of material classes. Okay, so fine. Thank you so much for your active participation and the interactive session, for making this an interactive session. Anything else you want to tell me, then let me know. And I'm ending this session. Okay. Okay. So thank you so much. Thank you so much.